Okay, so I stumbled onto something really weird with a code benchmark recently, and honestly, it kind of broke my brain a little.
Oh, yeah. What was it?
You take a big array, fill it with random numbers, right?
Uh-huh.
Then you run a simple loop, just summing up the numbers that are, say, greater than a 128.
Okay, standard stuff.
It took around 11, maybe 11 and a half seconds on my machine. But here's the crazy part.
Go on.
If you just sort that exact same array first, then run the exact same summing loop, it finishes in under 2 seconds, like 1.9 seconds.
Wow. Okay, yeah, that's a six-fold speed up.
Yeah.
That is definitely not intuitive.
Right. Logically, the order you add numbers shouldn't matter. So for this deep dive, we really need to figure out why sorting suddenly makes things so much faster. It seems to come down to something called branch prediction.
Exactly. It's a fantastic example showing that performance isn't just your algorithm, the big O notation. It's also about how well your code plays with the underlying hardware, the microarchitecture.
You mean like the CPU itself?
Precisely. Modern CPUs have these really long instruction pipelines. Think of it like an assembly line for processing commands, maybe 10, even 20 stages long.
Okay, so it's efficient if it stays full.
Right, but if it encounters a conditional branch, like your if deadheck 128 statement, the CPU can't wait to see the result. It has to guess which way the code will go. Will the condition be true or false?
Ah, the guessing game, like that railroad junction operator trying to predict if the next train goes left or right based on past trains.
That's a great analogy.
Yeah.
And just like the train operator, if the CPU guesses wrong, well, it's bad news.
How bad?
It's pretty devastating for performance. The CPU might have already started processing, 10 or 20 instructions down the wrongly predicted path.
Oh, wow.
So when it realizes its mistake, it has to completely flush that pipeline, throw away all that speculative work, and rewind back to the branch point to start down the correct path.
That sounds like a huge time penalty.
It is a massive penalty, measured in clock cycles. And in a tight loop like yours, those penalties add up very, very quickly.
Okay, I think I see the connection now. With the unsorted random data.
Yeah, the condition data equals 128 is basically a coin flip. True, false, true, false.
Yeah.
It's unpredictable.
So the branch predictor is just guessing randomly and getting it wrong about half the time.
Pretty much. A misprediction rate around 50%, and that's why it took 11.5 seconds. Constant pipeline flushes.
But with the sorted array.
Now the pattern is incredibly simple. First, you'll have a long, long run where the condition is always false. All the numbers below 128.
Right, like false, false, false for maybe half the array.
Exactly. And then suddenly it switches to true, true, true. For the rest of the array, all the numbers 128 and above.
N, then T, T, T.
Yes. The branch predictor learns this pattern almost instantly. After maybe one or two initial misses, it predicts correctly nearly 100% of the time. No pipeline flushes.
And that's the 1.9 seconds. Wow, so does this mean we should just sort everything before processing? It seems expensive.
Well, that's the trade-off, isn't it? Sorting itself takes time. O(n) log n. If you only process the data once, sorting might actually be slower overall.
Okay.
The real insight here is that the problem is the unpredictability of the branch, which depends on the data. So what if we could get rid of the branch altogether?
Eliminate the if statement. How?
There are ways, sometimes called branchless programming. Instead of if condition sum plus value, you could use something like the ternary operator.
You mean like sum plus itac equals 128 sum point 0?
Exactly that. Or sometimes bitwise operations can achieve the same thing. What often happens is the compiler can translate that into a special CPU instruction.
Like what?
On architectures like by86, there's an instruction called CMOV, which stands for conditional move.
Conditional move. So it moves the data only if the condition is met? But how does that avoid the branch?
It's clever. It essentially calculates both possible outcomes, adding the value or adding 0, and then based on the condition, it just selects the correct result to commit. There's no jump, no guess, no prediction needed.
So no chance of a misprediction penalty.
None whatsoever. It sidesteps the whole branch prediction mechanism.
And the performance, if you benchmark that code.
It's usually very good and, crucially, very consistent. Around 2.5 seconds in those C++ tests. Whether the data is sorted or random, it doesn't care about the data pattern anymore.
That's almost as fast as the sorted version, but without needing to sort first.
Precisely. Now, it's worth mentioning, sometimes modern compilers are smart enough, especially with high optimization flags like Natu3, to do this conversion automatically. They see your if statement and turn it into a conditional move behind the scenes.
Oh, nice. So the compiler can save us.
Sometimes, but you can't always count on it. Different compilers, different versions, different optimization levels. They might not all catch it. So understanding why the branchless version is faster is still really valuable.
Yeah, knowing about the hardware underneath really matters. Finding these kinds of subtle optimizations, whether it's low-level stuff like this or even figuring out how to apply AI agents and automation effectively, it takes real expertise.
It absolutely does.
And speaking of expertise, this deep dive is sponsored by Embersilk. If your business or even you personally are looking into AI, maybe for training models, software integration, or just figuring out where automation and intelligent agents could make the biggest difference, Embersilk can help.
They really know their stuff when it comes to applying AI effectively.
Definitely. Check them out at embersilk.com for your AI needs.
You know, the big takeaway here is just how much the physical hardware, the microarchitecture, impacts performance in ways that pure algorithmic complexity, your big O notation, doesn't capture.
Right. Sometimes knowing about branch predictors and pipeline flushes is more important than shaving off a few instructions in your loop logic.
It really drives home that software performance is this deep interaction between the code you write and the silicon it runs on.
Absolutely fascinating. That tiny detail about data order, saving dozens of clock cycles per loop iteration, mind-blowing stuff. Well, if you enjoyed this look into why sorting can unexpectedly speed things up by 6 times, please subscribe to the show.
Yeah, let us know what you think.
And hey, if you really liked it, leave us a 5-star review. It genuinely helps get the word out about these deep dives. Thanks for tuning in.